Hello, good morning. So today we're going to be looking at implicit functions and what makes them different from explicit functions. We have been working mostly with explicit functions, and I'll explain what that means in a bit, but it means what we think it means in English, which is clearly as stated. It's explicit, whereas implicit means more implied, right? We have to kind of read into it and interpret what might be at play. So we're going to look at what makes something implicit versus explicit. Given a description of a function, we might look and see what's the more natural choice just based on our own intuition, background knowledge on a subject. Maybe there isn't a clear choice. Our first example will actually be highlighting this issue. And then how we actually are able to solve for one variable as an explicit function of the other if we can. Sometimes it's not possible, and I'll show you how that works. So what I first wanted to do is show you a couple examples of implicit functions. So one example from physics, which is a very famous equation, F equals ma. You see those little arrows over the variables. That just means that they have a direction. They're called vectors. They're still variables though. Force equals mass times acceleration. So this can be rewritten in several ways, right? Is it that the force is equal to the mass times the acceleration, and that's that? Or could we also say that the acceleration is a function of the force and the mass? This is a multivariable equation, and this is usually where these things come up. Typically, we're just working with single variable equations or two variable equations. But if there's two or more, this question comes into play a lot. What's a function of what? And a case could be made for either or. So is force a function of mass times acceleration? Or is it that acceleration is equal to the force divided by the mass? Right? If we were to just solve for A. So this is possible, and depending on the context, this is something you might care about, right? Depending on the theory you're trying to prove or the data that you have in front of you, we might care about how we're defining the function. What depends on what? In behavior analysis, this is something that my brother studies. We were just looking at this equation the other day. This is a measurement of the change in learning of an organism. So the change in the learning of an organism is equal to some positive learning rate times the difference between the value that they get from the behavior versus their expected value of the behavior they chose. Right? So an example would be if I decided to go out and hunt for or search for this certain type of fruit, I have this expected value on that behavior, and if it ends up that that's greater when I get there than what I expected, I'm going to have a positive net learning of a new behavior, right? So instead of sitting around and doing what I normally do, if I found a piece of fruit that was really, really great, now I'm going to adopt that as a new behavior. So anyways, this is what that equation basically says. And so since there's several variables, we might be interested in maybe what this positive learning rate must be for this context. So I might solve for R and say, well, that must be equal to the change in the learning behavior over the difference in those values. Or we might be interested in solving for this B value inside, right? What must my value placed on this behavior be based on all the other factors that are here? So again, the possibilities are kind of endless, and depending on the context, it changes how we talk about it. But this is just to show you that there's tons of examples. I don't expect you to understand behavior analysis or physics for this course, just to show you that there's real consequences of what we're talking about. So sometimes there's a more natural choice of how to express a function as explicitly a function of another variable. and sometimes there's not. So let's take a look at an example here. So let's say we have a situation where Aaron and Chantel need to complete a project, and the only requirement, or one of the requirements, is that they both work a total of 100 hours on it. So if E is the number of hours that Aaron works and S is the number of hours that Chantel works, then we know that E plus S must equal 100. Now, it doesn't need to be a fair division of labor. That's what makes this problem interesting, right? We just know that E plus S needs to be 100 hours. So the question is, is Chantel's time to work a function of Aaron's hours, or the other way around, or neither? So is Chantel's time to work a function of Aaron's hours? So typically with an explicit function, we'd have something like y equals f of x. Y is a function of the input x, and we might have some rule like 2x plus 1. Y is explicitly a function of x. And again, one shortcut kind of way you can think about it is they're each on opposite sides of the equal sign. Right? I have y equals on one side and an expression of x on the other side. So these are like the kind of two key ingredients. If we can't write it like this, then we can't write it as an explicit function. So can we do that with this here? We have two variables. Can I write one as a function of the other? So is Chantel's time to work a function of Aaron's? Well, if we have E plus S equals 100, we could solve for S to get it into this form, right? So how would I solve for S? I would subtract E from both sides, use the balance principle, and I'd get S equals 100 minus E. So here, yeah, we'd see that S is a function of E, and we can write it explicitly like this. But couldn't the same case be made for Aaron? But also we see that E, by the same logic, would be equal to 100 minus S. The number of hours that Aaron works is going to be the difference between the 100-hour requirement and the amount that Chantel works. So if Chantel completes her work and she does 40 hours, Aaron would have to work 60 to finish it up. So here it's not necessarily clear which is a function of which. Not clear. A case could be made for each. And we can solve it like I just showed you down there. And what that case is that the number of hours Chantel needs to work depends on the number of hours Aaron works, and vice versa. Okay, so we could write E as a function of S. We could write S as a function of E. Let's look at something where maybe it's a little bit more of a natural choice, what depends on what. So here we have an example between two variables. The amount of money made at an event P is related to the number of tickets sold to the event T. And we're given this equation that relates the two variables. So we might be asked, what is a natural choice for the output or dependent variable and the input or independent? Another way to think of this again is like the cause and effect. Right? That's a rough estimate of what's happening with input and output. We feed the function the cause, and the effect is the result or the output at the end. So what makes the most sense? Well, if P was independent and T responded to it, right? The amount of money made, does the number of tickets sold to the event depend on the amount of money made from the ticket sales? That seems like a bit of a long walk, right? You could maybe make the argument that more tickets are going to sell because it seems there's more money being made from an event. Maybe it's very popular. That's possible. Or how about the amount of money made depends on the number of tickets sold, because the number of tickets sold will then tell you how much money you're making. So it seems like a more natural choice that the amount of money made would depend on the number of tickets sold. The number of tickets sold is independent. It doesn't depend on any factors that we see here, whereas the amount of money made does depend on the number of tickets sold. So we might say that here dependent choice would be P, and the independent would be number of tickets sold, T. The amount of money made depends on the tickets sold. So P as a function of T makes the most sense here. Okay, so P is a function of T, and that makes sense. And so now let's solve for P as an explicit function of T. So what that means is P on one side, expression of T on the other side. So we have to start with what we were given. What we were given was P minus 2T minus 100 equals 0. So if my goal is P on the left and everything else on the right, or you could have P on the right and everything else on the left, right? The idea is that we've isolated P. So I want to do that using the balance principle. So let's start by maybe adding the constant 100 to both sides. So P minus 2T equals 100. And then I could add this 2T to the other side. If I'm solving for P, balance principle says these cancel here, just like they did here. And we're left with P equals 100 plus 2T. I'll write that a little bit clearer here. And we have now a formula for P in terms of T. So anytime I have an input of T, I can find an output for P, right? So if the number of tickets sold was, let's say, 40, then I know the amount of money made is a function of 40 tickets sold, which is 100 plus 2 times 40, right, which comes from right here. And so that's 100 plus 80 equals $180. I could do that with any input and output, right? If I sold 200 tickets, amount of money made for 200 tickets would be 100 plus 2 times 200, which equals 100 plus 400, which is $500. Okay, so we, again, to relate to our previous sections, we see that f of, let me write this, P equals f of 40 equals 180. P equals f of 200 equals 500. And so as input-output pairs, we know these are really 40, 180. And this is, for an input of 200, we have an output of 500. So again, just kind of tying back to concepts we've already covered here. So this is how we would identify a function, an explicit function. Going for the more natural choice of what depends on what. Sometimes it's clear, sometimes it's not. And then just using the balance principle to solve for one variable, what we say in terms of another. So when you hear that, in terms of t, or in terms of x, it means just to have all the other numbers, operations, and variables on the other side of the equation from what you're solving for. So p in terms of t means p's on one side, everything involving t and everything else is on the other side, just like we have here. So let's say we have a value of an asset that's shared, and that's going to be related to the number of person hours of usage. So this could be a getaway, a boat, a fun car, something. Let's keep it fun, but it could be any asset, and it's really going to be related to how much can you use this asset. And so one unit of measurement for that is what we call person hours. It's the number of people times the number of hours of usage. So let's say we're given this equation. This relates this particular asset to the amount of usage. And we want to express v as an explicit function for h. Function of h. So we want v is some function of h. Really, remember, this is the function name, and this can be anything. And then we would need to solve this equation with v on one side and an expression of h on the other. Okay, so if we take 50 times h minus v equals 100h, we see that v is on the inside of these brackets. And so there's two ways to go here. One would be to ungroup and distribute this 50 through. But since I only have one term on the right-hand side, and this is just a scalar value, what would actually make the most sense would be to divide by 50 or multiply by 1/50th on both sides, right? Since the multiplication trumps the subtraction over here, this multiplication would happen here, and I would just be left with h minus v on the left. And then 1/50 times 100h will cancel with a factor of 50 and leave me with 2. So I'll be left with 2 times h on the right and h minus v on the left. Right? Because we divided both sides by 50 using the balance principle. And now solving for v, a couple ways to go. One would be to just subtract h from both sides to get rid of this. So let's do that. Minus h from both sides. And we're left with, on the right, 2h minus h. I'm left with 1h. On the left, remember that you're bringing along the sign of the term. This is a negative v. Right? So negative v equals h. I notice some students leave it here. This is not totally solved. Right? Because what we want is v equals a function of h, not negative v, or the opposite of v equals something. So what you can do here is just multiply both sides by -1. Over here, negative times a negative will just leave us with v equals the opposite of h. Okay, so here this is a pretty simple function, but what it turns out to be is that the opposite of h's value is v, or the value is the opposite of the number of person hours of usage. Now, does that make sense in the real world? Maybe. That's unimportant. What is important is that we can write this as an explicit function of the other variable. And that this is probably the most natural choice, that the value of an asset would be based on how much usage we get out of that thing, right? The other way around would probably be a longer walk or a less natural choice. So here, an example of maybe when we can't do this. So if we're being asked to solve for g as a function of t, here we've got some equation g squared plus t cubed equals 49. How would we go about this? Well, we really haven't even learned how to solve equations like this yet, so I'm gonna show you roughly how this would go. I don't expect you to have this down yet. We'll be looking at equations like this later in the course. But for now, let's proceed as we normally would, which is to isolate the variable, right? We want to isolate g and get it by itself and have everything else on the other side. So we want g as a function of t. So g on one side, everything else on the other. So how would we go about doing that? Let me pull this around. So first I might use the balance principle and subtract t cubed from both sides. Be left with g squared equals 49 minus t cubed. And now to get g by itself, well, I have g squared, right, which is really g times g. So to undo a squaring, I would need to take the square root of both sides. And what actually happens here, if you recall, and we'll go again into more detail on this later, that since -2 times -2, which is -2 squared, this equals 4, is also the case if we square just +2. When we take the square root of 4, there's actually 2 possible square roots, -2 or 2. And so what we do here is we say, well, then g is plus or minus the square root of 49 minus t cubed. Now this is really just to show you that, right, the positive root here squared would equal g squared, and the negative would do the same. They both solve the equation. But what this really means is you have two outputs. So this is not a function. Okay, so here, since we know that there's two outputs for each input, because how this really translates is g equals radical 49 minus t cubed, or g equals negative 49 minus t cubed. This really has two outputs for each t input. If I say t equals 1, it has to go in here and in here. And so that breaks down our definition of a function. We have to have one output per one input. We can't have two outputs coming from one input. So this is not an explicit function. Okay. When is this going to happen? It will happen with even powers like this, when we need to solve for an even power, because we'll get two roots that work. It will come up in other contexts as well. But I also want to be clear that just because you can't solve an equation doesn't mean that it's not an explicit function. So for an example, if I had, let's not use that, let's use 3 to the x minus 10 equals y, and I wanted to solve for x as a function of y. This is actually something I can do. Even though this is in the exponent, we don't have in this course, and you won't until actually pre-calculus, the ability to solve this equation as a function of y. So it is possible, but just again, we don't have the tool for it algebraically right now. So what you're still on the lookout for, if something's a function, is how many outputs does it have for each input. If the answer is 1, then it's still a function. If it's 2, like we saw up here with square roots and needing the positive and negative square root, that's going to be a problem. Okay. So a lot of times, you know, the challenge here comes in the mechanics of solving for the variable. And I'm going to give you a tip on this right now. Solving for one variable in terms of another. And you've probably seen me say this before, but if not, if you're getting lost in the algebra because there's too many variables and you feel like it's kind of like an alphabet soup, you got to remember two things. All variables are numbers. They're really placeholders for numbers, right? So any rule that works on numbers needs to work on variables. But the other thing that you can do is you can pretend as if, and this is a big skill in general in math, pretend as if, you know, t equals 5 and p equals 4 and y equals 3. Give them a value and work the equation as if they have this value. So in other words, if I had y equals pt minus s and I was asked to solve for t, and let's say maybe I'm feeling a little intimidated by how many variables there are, well, what I could do is take the other values, the other variables, and give them numbers and say, well, let's pretend that y is 5 and that, well, here we said y is 3. So let's stick with that. So y is 3, p is 4 times t, and s we'll say is 2. Just make up some numbers and then solve it like you would a normal equation, right? This looks much less intimidating maybe to solve than the first one, but really it's the same. So how would I deal with that? I would add 2 to both sides, right? And then I'd have over here 3 plus 2. and I'm not going to simplify it so that we can see something here. So I'd keep it as 3 plus 2, which we know in the back of our head is 5. And then to solve for t, what would we normally do? Well, we divide both sides by 4. So then this would cancel over here, and we'd be left with t equals 3 plus 2 over 4. 3 plus 2 all over 4. But then we can do a reverse substitution. We know that we actually swapped in 3 for y. Let's do this. We swapped in 3 for y. We swapped in 4 for p. And we swapped in 2 for s. Alright, so this was really s. This was really y. And this was really p. So we see, okay, t is really y plus s all over p. So if you act as if the variables are constant numbers, then you can kind of reverse engineer it or get a better sense of what it should look like. So that's kind of one of my pro tips as we're getting started, getting comfortable with these. Eventually, I do want you to just be able to tackle things like this. You'll see them as structures and patterns instead of just a jumble of letters. But this is a nice, kind of like, not training wheels, but something akin to that. It's just a good way to view it because really the variables are numbers. So that's where we'll end for this section. I might have one smaller video coming after this, but we've got everything taken care of here. Implicit versus explicit functions. If there's a natural choice, then we can choose that as the input and the output respectively, and then how to solve for one variable as an explicit function of the other. We know how to do this in general, and again, if you get lost in the alphabet soup, to try as if these other variables have numbers, and then go back and erase and find how it actually should work out. So I hope you enjoyed this. Implicit functions are, again, they have tons of applications in the sciences. We work with this a lot in multivariate calculus. I know you guys aren't there yet, or maybe not even planning to get there. But just to know, this is a fundamental idea that scales up really big. Okay. So great job. We'll see you in the class discussion.